It's my pleasure to introduce our uh, next talk. This is a student problem C, how to catch a treat. And Connor and Lucas will talk about modeling the simulation of physical system in MATLAB Simulink and Simscape. Okay, without further ado, let me turn the stage to you. Thank you.
Okay, thank you. So we just completed the the SCUDEM problem C, for how to get Fritz to catch a treat. And the entire thing was off of modeling a system of equations to actually to ascertain whether or not it's easy for a dog to be able to catch an object flying in the air, all the variables and factors around it, including stuff like drag, the size of the object, the dog's mouth, the angle, and all of that encompassing the entire problem is what we were really solving. And we're kind of today breaking down our methodology and how we solved that, as well as how we use certain tools in MATLAB to achieve a desired output. So we first started with the base modeling of the system of equations, gathering our variables together and actually solving the differential equation down to something that we can actually use in modeling and in our MATLAB simulations. For this equation, we included all factors that we were using: drag, the shape of the object. We had a couple different object shapes, such as a slice of pizza or a donut, different masses and
Can
stuff
I
like that.
quickly ask, you said you have one page of slide. Do you want to share, or we are just gonna, or we are okay with this? Sorry for interrupting.
No, you're perfectly fine. I was trying to find the PowerPoint, and I can open up what we have so far. It doesn't look like I am not able to find the full complete PowerPoint for whatever reason. I only have our mathematical modeling slides, but I don't have the
Okay.
very last slide that include the MATLAB Simscape, but I can share these slides and go through them if that helps.
Well, whatever works best for you. I'm sorry for interrupting. Just go ahead.
No, you're fine. I'll go ahead and I'll share it because I know that visuals can really help. So let me go ahead and share my screen. Okay. So are you able to see this?
Yes, yes.
Okay, perfect. Now I'm just making sure. Okay, cool. So we're talking about the projectile motion with air drag and the different steps that involves getting the air drag. And we start with first the horizontal equation, because horizontally it's actually quite simple. You only have one velocity direction, so the drag's always going to be going the opposite direction of your velocity. And you can kind of have your velocity going positive and your drag going into the negative x direction, as noted over here with with this graph. You also have your initial angle, which can change your initial velocity into your velocity x and velocity y respectively, as well as we added an initial height variable for the person who's throwing this object for the dog to catch. Breaking down the equation for the x direction was the first step because it was easiest. And then, oops, sorry, I forgot the slides had a voice. Next, we broke down the vertical, well, this is the complete breakdown of our horizontal trajectory. And this shows everything for the differential equation with us solving the general and particular solution for just the horizontal trajectory currently. If you can see up here in the upper right corner, we have our velocity denoted by Vx and our drag by the drag coefficient times x dot. Like I said, for the horizontal trajectory, this was very easy because our object is always flying forward, meaning drag is always in the negative x direction. However, as shown for the next part, which is the vertical trajectory, it's much more difficult to ascertain because initially your object is flying vertically in the air, meaning the drag is pushing down on it. However, after a certain peak, when the object starts to go down, the drag is pushing up on the object. So this mathematically is still okay because if you have of directional velocity, then if your drag is negative that direction, mathematically it equals out. You just have to know at a certain peak, it's going to change directions, and that can make simulating things much more difficult. Simulations that we did included MATLAB Simscape, which I apologize for not having the video of. Maybe if Lucas does, he can share that. But for the MATLAB Simscape, a lot of these factors is where it really became important, because MATLAB Simscape is more for the visual side of things. We found a CAD model for a dog, and we split the model up into various pieces that we could then manipulate, such as the head and neck angle, the jaw opening and closing, and we also were able to control the body so that it could move vertically in the air. All of these factors, and especially for the system of equations, was really important in getting the data for our Simscape model. We have to, in the Simscape model, put in the broken down system of equations to get the object to fly. And then we also have to solve where should Fritz be and how open should his mouth be to catch the object, and then put those equations into our model of Fritz to see if he could catch it or not. I'll go ahead and go through to the next slide, which is more of our, or not. Like I said, this PowerPoint isn't complete. If Lucas has the other one, the more complete version, I don't know why I have it, and I apologize for that, why I don't have that PowerPoint. But that other part of a PowerPoint has more of a breakdown graphically. We have a couple more graphs in there. We also have the video of our Simscape model. All of this is also shown on the YouTube link that I believe is posted on Simuoid's YouTube channel for the entire presentation. That goes through everything we did. I'm now going to kind of break down further the Simscape part of it, because that's what really made our project unique, in my opinion.
Connor,
Yes, Lucas.
could you open the YouTube video so they can visualize it better?
Sure. I'm going to stop sharing my screen so I can go and grab the YouTube video, and I'm going to show the very, very tail end of it, where in that part, it talks about the dog catching the object using Simscape. So for anyone who doesn't know, Simscape is a visualization software within MATLAB and within MATLAB Simulink, and it allows you to use a multi-body simulation to be able to obtain some data, some physical data about something. For instance, you could have a physics problem, like a ball being thrown, and within Simscape, it can simulate that ball going through the air, the physics of it. It can simulate it bouncing on the ground, the distance it would travel based off of an initial push, and other things such as that. Okay, I have the video pulled up here, and I will go ahead and start sharing my screen and go through the Simscape portion of the code. Okay, and okay. So hopefully everybody can see this, yes?
Yes.
Okay, perfect. So this is some more of our code for the visualization. These are the last couple slides that I, for some reason, have in my PowerPoint, but I will go through them now. Okay, right about here. So this was our visualization using just graphs in SolidWorks, gosh, in MATLAB, graphs in MATLAB. We plotted the trajectory of the particle, as well as roughly the position that Fritz's mouth would have to be, with 2 lines denoting lengths for it to catch said object. This shows Fritz jumping up by 50 centimeters, rotating his neck by 75 degrees, and opening his mouth by 45 degrees. And all of those numbers we obtained from looking on the internet for real world data of how high do golden retrievers jump, approximately how much can their neck rotate, and how much can their mouth open. One thing that we've gotten very accustomed to, especially at KSU, is being able to obtain real world data to make our simulations or our projects more realistic. And this is just one example of it. We have data like this on the internet and we can use it. And in doing so, it makes everything way more detailed and exact. And we don't have to do any guesswork or approximations. So after that, we then started plotting multiple graphs to see the effects of different changes in our system of equations. So the first one is an angle of attack change and how the angle of attack influences the area of where does the particle fall. So as you can kind of see, there's a cluster over here in the center that most particles will fall within a certain region with a varying angle of attack. This cluster shows if someone's randomly throwing an object, tossing it in the air, no matter what their angle of attack is, if you are within this region, that has the largest number of pathways for the particle to travel through, and you're most likely to catch the object if it's within those regions. So therefore, that's the region we say Fritz should stand in. If he's planning on jumping in the air, then he should probably be about 1.2 to 1.4 meters away. If he's not planning on jumping in the air and catching it from the ground, maybe approximately 1.6. The next graph that we plotted right here, this one shows when Fritz should jump and timing. So this is the particle being thrown at different points, and I was trying to estimate when he should jump time-wise. So this is the location that Fritz needs to jump at to be able to catch certain particles. Right here on this graph is the exact location that all of them converge into one point. So if Fritz doesn't know the velocity that a particle is traveling at, for instance, if he can time his jump right, he can jump where all the particle paths would meet in one. But this is really difficult for even us to be able to calculate and to think about without displaying it in some way. And the amount of work that we just went through to make graphs of this in MATLAB and obtain data and systems of equations goes to show the amount of thought process that Fritz and any dog really has to go through to catch an object in its mouth, and to be able to do it without failure, tremendously difficult. And us displaying these graphs and this entire project was kind of us showing that expecting certain things out of a dog, for instance, perfectly catching something you throw in the air, can be unrealistic, as I don't think us as humans could do these calculations all in our head without some graphical interface. This very last part is just us showing the different objects that could be thrown and their effects. As you can see over here on the side, the effects of the different objects, shape, mass, drag coefficients even, is very, very minimal on the path line. The path line stays pretty consistent, meaning that the object should fly pretty similarly. There's certain things you can't really calculate for. For instance, if you're throwing a slice of pizza, there's a chance that the shape of the slice of pizza causes lift and could cause a different path line. This, however, would have to be done extremely experimentally because, for instance, you can't go online and find the coefficient of lift for a slice of pizza. So for us, we just stuck to drag because drag varies based off of your area and very, very slightly on drag coefficient, as well as the mass and the size. So given all of that, we were able to determine that most objects are going to have a pretty similar trajectory, regardless of what they are, their shape, size, and mass, etc. So next up, we have our Simulink model. This is a breakdown of the system of equations that denoted the y and x position of the actual particle as it flew through. And for anyone who hasn't used Simulink before, this can all get pretty confusing and or overwhelming, but it's essentially kind of similar to when you connect wires. We connect these lines together, and that carries a an input. So we have right here integrator blocks that are able to integrate our force via our gravitational acceleration. And the force that you would get from things like when you throw it or the force of drag. And we integrate that into velocity. The velocity then goes into our input for our drag, and this creates a loop. Once that is then integrated once more, we get y position. We then do the same thing for x position, just with no constant acceleration of gravity. So it's just the loop of drag that then gets integrated into your x position. Next up is our actual Simscape portion. So for Simscape, we broke it up into three different components. We had, or three different subsystems. We had the calculation subsystem, which I just showed you. It does all the math and everything. We then have the visualization subsystem that does the 3D visual representation of the object flying through the air and the dog trying to catch it. And we have our graphing subsystem, which, as it sounds, just kind of graphs it similarly to graphs we showed before, just it graphs it more in real time so that it's easier for us to manipulate it without having to rely on the visualization part of it. And then over here to the left is just more of our visualization software and the amount of Simscape that had to be done to get the visualization. Multiple blocks were used. We have multiple times right here. There's a from file solid block. And the from file solid block is how we got Fritz's body, or a golden retriever, into Simscape. Is we found a CAD model that we imported into SolidWorks and then imported that into Simscape. And so that's how we're able to get complex geometries, such as a golden retriever, into Simscape. And when you combine it all together, you get an end product that will look something like this, where you have a shape like a slice of pizza jumping in the air and a dog's mouth catching it. And this was really what I like to hone in on, because this is what makes our project different from a lot of others. And we just have the simulation stop when the dog catches the slice of pizza, but even a couple seconds, the fact that all of this is done in MATLAB and you're able to visualize it and display it is truly what I love about the Simscape software and the stuff that it can do, because it truly is unique. I would struggle immensely to try to make something like this in SolidWorks, for instance. And in Simscape, I can take data from this and export it directly to MATLAB where I do calculations. Oftentimes, for instance, if I have a 3D system, I can model a spring and a block, make a vibration between them, and then measure the output. And I can obtain things from that output, such as your natural frequency or your spring constant. And this is what we do a lot in our research lab, is that we're able to take data from MATLAB Simscape of flexible bodies and turn it into spring coefficients. And because of our usage of compliant mechanisms, this is what makes MATLAB Simscape invaluable to us. Because without it, we really couldn't get those spring coefficients otherwise, especially for complex geometry springs. So that's just a little bit about our project. I don't really think I have anything more to go into, except for if anyone has any questions about Simscape that we can answer. Lucas, if there's anything else that I missed that you might want to add.
No, I believe you covered everything.
Okay.
This is really great work. Thank you. So do we have any questions from the speakers by any chance? If not, I actually have a question first, because this whole thing, I mean, I use MATLAB for my research on a regular basis, but I don't, as a mathematician, I don't really use Simulink, and I'm not familiar with Simscape. So can I just ask your background first? Like, which year are you in college? I guess college, right? And also, what's your major? You said research lab earlier. So like, can you say a few more words about both of your backgrounds, please? Thank you.
Yeah, sure. So I guess I can start and I'll let Lucas obviously
Yeah.
talk about himself. So last year or last semester when this project was going on, I was finishing up my undergrad in mechanical engineering. And I graduated from that in December, right around when we were finishing up this project. Currently, I'm in my PhD in interdisciplinary engineering, also at KSU still. And so that's mainly my background. I do a lot of work in smart robotics, compliant mechanisms, but my background is mechanical engineering, and that's where I started to use MATLAB the most.
Yeah, my background is also mechanical engineering. I'll be graduating this fall, and I've been working with Dr. Takesh, Dynamics and Controls Lab for a while, and doing mostly Simscape. That's the last part that Connor showed you. And I'll be probably pursuing a master's degree, also in mechanical engineering.
Great, that's really good to know. So the last session I'm moderating on another session. All the students they are all also from mechanical engineering. That's
Mhm.
really, they also get outstanding awards. So that's really impressive. So do we have other questions from the audience by any chance?
I tuned in late because I was, with several sessions at the same time, it's really hard. And most of them were only 10 minutes, and I'm glad that this one was longer, so I still got to see it, and I'm dying to see the rest of it. So one question I have is a technical question. I can do captions, but I can't seem to get the transcript up, and I have gotten transcripts up on other talks. Do you know, Yaping, if there's any?
So the transcript will be made available, I believe, after the recordings were done. It should be automatically generated by Zoom, since they are all Zoom recordings. So they will be available later.
Good.
Just yeah. So
And
don't
I'll
worry
be
about it.
anxious to see the rest of this presentation because I just love this animation that I saw. I can see that the authors were already familiar with what seems to me to be an incredibly complex software, but I'm glad to know that's where the younger generation is heading.
May I also ask how complicated it would be if we were to change? I think this is a pizza here, right? So if we were to
Right.
change it to an apple or a hot dog, like for other, did you run simulations for those or so? Or just
So
curious?
I just chose a slice of pizza kind of randomly. But to go through everything, so in the most simplest terms, right here, right about here is this block called the extruded solid. With the extruded solid, you essentially just tell the block a couple different points in the clockwise direction, and it makes a shape that you then extrude a certain distance. I
Cool.
could, however, change that block into a spherical solid for an apple, or a revolved solid if I wanted to make a donut. So we can make a bunch of different shapes. I just chose a slice of pizza mainly because getting rotation while it's like going through the air, making it rotate is something that can be oftentimes very difficult. So I chose an object that people would not necessarily expect to rotate as it flew through the air.
I like that.
Other than that, everything else, we've got this down here, which is our brick solid for the ground. And then this system over here is our system for Fritz, which is a bunch of different body pieces connected by revolute joints to give them motion. All of
Cool.
the splitting up of the solid we did in SolidWorks. So we had a SolidWorks, a 3D CAD file that was of a golden retriever. And we then took that and we used the split command in SolidWorks to split it up into different body parts and save those as different files. We then bring those different files into MATLAB and just stick joints on them to make them function. Obviously, you can split the model into even more parts. So if we really had, I guess, more time, we could have split the legs into different pieces to actually make it move like a dog would and jump in the air. However, we felt that for the amount of time we had and the fact that Simscape was kind of our last priority, we just made the body rigid and actuated other things such as the head and neck.
Well, thank you for that explanation, walking me through what you did. It's marvelous. And I can see that because you're both upperclassmen, you've had a lot of experience with this, so it would be easy for you, but you made it so that I could follow what you were doing, and that's not easy.
Thank you.
Yeah.
One of my main roles in the research lab is teaching this software to a bunch of the other lab students, because it's something that we pass down in our lab. Essentially, it's knowledge passed down from generation to generation. Even our lab supervisor, our professor, she doesn't know how to use Simscape. She just knows that the students do, and she knows that she wants to use it. So she lets us pass that knowledge down. So I've definitely had practice at explaining this. The last thing that's kind of important about the model is right here is a force block, a spatial contact force, which essentially is just when two things collide, it outputs a force. And I simply put in to make the animation stop, because the simulation time is usually quite large, especially for something like that. So I made it that when a force is sensed between the pizza and the dog, it stops the simulation entirely. So that way it wasn't, because we had a simulation one time where we left it for a couple hours and it hadn't moved, but the pizza was just sitting in the dog's mouth. It was just going through and taking its time. So I added that in so that we didn't waste time with long simulation processing. But there's definitely some neat things you can do in Simscape.
Right. Actually, what you were talking about is actually my last question. I know you must be very familiar with Simscape, but can I ask, just to have a very brief, maybe stupid understanding? So after you have your idea what you want to put into this model to build this Simulink thing, how long does it take for you to finish this whole thing? You show us here, and once you build it, how long does the simulation actually takes to just produce what you were showing us towards the end of the talk, like time-wise, assuming like a common laptop, like not a very fancy computer, and just
That depends on the complexity of what we're trying to do.
okay.
Yeah. So there are a lot of factors that go into it, and there's a lot of things. For instance, I always use like coding and electrical engineering as an example. Oftentimes they have a different person program a device versus the person that wires the device. And the person who programs it will have to spend more time depending on how the person who wired everything up. Similarly, for Simscape, depending on how the SolidWorks file was made, depends on how much time and effort it'll take for me to finalize the Simscape model. Because when you import from SolidWorks, you can import an entire SolidWorks assembly as an entire Simscape model itself. And it's the import function and the way that MATLAB has done that, it's really, really amazingly good. But also there's some problems, and all of the problems are all user error. But essentially, it'll take anything exactly as it is in SolidWorks and make it that way in Simscape. If parts in SolidWorks are allowed to be able to rotate, Simscape will allow them to be able to rotate. This also means, though, if someone else gives me a SolidWorks file and says, can you make a Simscape model out of this? If they constrained things so that two pieces are always 5 meters apart, it'll become very difficult for me to have to change that if that's not how the part's supposed to behave. So it really does depend how long it takes me to make the model off of how somebody assembled the whole thing. For this model, it didn't take me a lot of time because I made it so that the dog was completely rigid and I gave it the motion that I wanted in Simscape. That way, it doesn't throw in joints that are not needed. For instance, if two parts are allowed to move in the X and Y plane and rotate in the Z direction, it'll put that exact joint in your Simscape model. And that can kind of just create confusion when I'm going through the model and trying to perfect it and make it move properly. So usually I just start off with a rigid SolidWorks file, SolidWorks assembly model, and then I put the motion in Simscape. But I know I've had problems in the past with the way things are constrained in SolidWorks, makes it a lot longer time for me to actually make the Simscape model. Otherwise, there's plenty of things you can do when you're actually running the simulation to reduce runtime. Most commonly, we'll have runtime issues, and they are kind of out of the blue. Your model is either very, very fast when it runs or very, 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 very slow when it runs. And generally, the slowness is kind of, oh, you added in certain springs and they behave just perfectly enough that it takes hours to run a simulation. And then you can reduce K value and it takes minutes. So it's kind of playing around with it to see what you need. Depends on how long it'll take. If you need a certain K value, then it might take hours. But if you just need a range of motion, you can reduce the K value on the springs and it might take minutes. So.
Okay, thank you. Thank you very much. So we are running out of time. If anyone have questions, you can stay here. This room would not be closed unless all speakers left. But thank you very much. This is really good work.
Thank you also. I agree. Really good.
Thank you.
Okay, bye.
Thank you.
Bye.